So what we've been doing is on Friday, we looked at this idea that I could have a charge at any given position. And I could look at a test charge at some other position, and we could calculate an electric field. And we had defined our electric field as the force divided by that charge. So we could look at my electric field a little differently. And that simplified things because this would simplify into K, Q, R squared, R for our point charges. But then we said, well, wait a second, we could do this. We could do this as distributions of charges. So I could look at a disk and look at an electric field at that point where this was a distribution of charges. So when you guys are getting into Calc 2, and as you are moving through Calc 2, you're starting to do integrations where you're looking at, if I'm looking at incremental masses over a sphere here, I can integrate these incremental masses to be able to get the entire mass of the sphere. Can't spell. I can do that. And so that, and this one, of course, is going to be a 3 integral because you're going to do it over the X axis, you're going to do it over the Y axis, and you're going to do it over the Z axis because you're going to be looking at a volume. And if I'm doing that, I'm going to be doing a density, which is a mass per unit volume. And we would be looking at it by our little incremental volumes. So I don't know if you guys gotten to 2 and 3 integrals yet. But basically that's what you're doing. Okay. Because remember what an integral is. Basically an integral is just a fancy sum. And all we're doing is rather than doing the individual charges, we're going to do a distribution of charges. So I could look at a linear distribution. Usually we do this, and this is a charge per length, DL, and that's what we did on Friday is we looked at a line of charge. And we sort of did it over a rod looking at that. So what happens when you're dealing with your calc is you're going to be doing these triple integrations, these double integrations, but basically all you're doing is you're summing up to go to these infinitesimally small items. Because what we want to do is we don't play with individual point charges, we play with charge distributions. That's what we do. We don't, and when you guys get into dynamics, you're going to be dealing with rigid bodies because up until now, all we've been doing, usually if I have an object, right, we have an object, we always work with the object at its center of mass. And we always looked at whether or not we had motion that was going this direction. We always looked at that center of mass piece. And that's where we're starting to deal with that calculus item. So when we're starting to look at this, now we're taking into, and this is what we do in physics all the time. We start with a simple case and then we start to expand it. So we're going to define this idea of flux. So we know, because that was one of the things we were doing on Friday, is we were dealing with our lines of force or our lines of our electric field. And we could represent that electric field. The strength of the electric field is in that number of lines in our area. Now I've drawn a uniform electric field here. And this is where things get fun. And you have to start dealing with things a little bit. I can look at a plane that's bisecting my flux here. So my plane is here, and I've got my lines. I've got my lines of electric field are going through my plane. And I'm going to try and kind of, so this is my plane. And right now I've got things that are kind of perpendicular to the plane. So there's my plane going through here. And I've got my electric field is represented by my lines. And this is just an arbitrary plane that I'm looking at. What we're going to do is we're going to define our flux. So we're going to define flux. We're going to use this big capital Phi. And this is going to be flux. And really what we're looking at is the number of lines that are going through the area of the plane. So I've got that plane that's bisecting it. It's perpendicular right now as we've drawn it. It's perpendicular. And we have that area of the plane. And that's going to be our electric flux. Now, one of the things that we know is we can move this plane anywhere, right? And if I have it perpendicular, so we're going to make the observation, the flux is going to be maximum when the plane is perpendicular to the field lines. Now look what happens if I draw my plane a little differently. Now if I draw my plane parallel to the field lines, the flux is essentially zero. So we get the flux is equal to zero when we've got that. Now, this looks like something we've seen before. If I have a vector that's an E and I have my area and I do a dot product, what happens is this now becomes E a cosine of my angle. So we got their calculator handy. because I didn't bring mine down today. Do the cosine of 90 degrees. Cosine of 90 degrees is 0. Sine of 90 degrees is 1. So if this is 0, then cosine's 1. Is that right?
Well,
Do the cosine of 0. Okay. Yeah. So that just so to remind everybody, this is going to be when the angle is equal to 0. This is when the angle is equal to 90 degrees. Because it is a little backwards. All right, it is a little backwards. Now we can play with this lovely, right? We can play with this lovely and we can manipulate the surface, but we know that the number of lines that are going to cross through that surface is going to be different depending on how we do that. So that's where Guass starts to come in. So what he's going to look at is he's going to look at the flux. And this is going to be electric flux. Is going to be equal to the sum of all the electric fields times my little incremental change in area or I can represent this as an integral about the surface. And that's going to be my E dot product A. But my electric field is going to do weird things. So I'm going to move that. My electric field is going to have magnitude. Now I'm going to deal with this. And I'm going to use this symbol to represent a closed surface. dA. And what that ultimately is going to come out to be is that my electric flux is going to equal the charge enclosed divided by the permittivity of free space. And that's enclosed. So we can go through all kinds of horrible manipulations to deal with our charges. But ultimately what's going to happen, as long as if I don't have a charge enclosed, my electric flux is going to be, it's related to that. So what that means is, here's my Gaussian surface, and we usually use spheres. If there are no charges inside, no flux. If there's a charge inside, I'm going to get flux. And the direction of that flux is going to be dependent on the type of charge that I have. And that charge enclosed can be a net charge. So as long as I got 0, that flux is 0. If I have -3 Q, my flux is going to be 3Q divided by the permittivity of free space. So it comes down and plays with that. Now, this gives us some interesting ideas to play with. One is that if I have a device that looks like this, the charge is going to concentrate on the point. It also, if I have a conductor, the charge is going to be on the surface of the conductor. So it's going to give us that charge of the conductor. What this is going to do for us is a couple of things. If I have a line of charge, I can develop a uniform electric field. If this is a negative and that's a positive, I can develop uniform electric fields between two parallel plates. And this is going to be an important thing that we get. I'm going to do a couple of things here. I'm going to switch over. So these are some visuals showing how the flux is going to play as we deal with the charge, and how the flux, now my Gaussian surface starts to play with it. So we're dealing with that EDA in order to get those animations. So you have lots of, this is electric field lines around a point charge. It's so there's a lot of GIFs in here looking at your dipoles of charge. This is flux through a box. Is it showing? Huh? It's a different tab. No, that's the Gaussian one. I had trouble with this one a while ago too. These are embedded ones. And this is the one that will show you the plane. If you play the flux through a loop, that one will show you that the plane one. Ever since they moved to the HTML5 or something, these have not been as nice to work with. This particular set of GIFs has not been as great, but this is my electric flux. This is another one that's got the plane that goes back and forth. So depending on how I'm changing the plane, the size of my plane will change the flux. The orientation of the plane will change the flux. But what it ultimately comes down to is you're looking for the charge inside your Gaussian sphere or your Gaussian distribution. That's really what you're looking at. And as you see, what's happening in this one is essentially we're moving the plane, the area of the plane is staying the same, but we're moving further away from the charge. And so you get the nice changing in the flux that you get there. So you want to look at the net charge inside the Gaussian surface. And the problems will ultimately, there's my electric field visualizer. I think that's another one. This one is kind of cool. If you want to play with your electric field visualizer, that's another one that's kind of a neat one to play with, to look at electric fields. Now, so you're asking me what's important about it. Well, the big thing is knowing what's inside the surface. And I have yet to ever use it other than to help us define our devices. We will also use Gaussian surfaces for magnetic flux, and the magnetic flux is going to be more important than the electric flux, because the magnetic flux and the electric flux are actually, we come together and we bring them together in Maxwell's equations. But the magnetic flux is time dependent, the electric flux is not. And that's where we're going to start getting our wave packets that are in there. So I've provided some other modules to help. Oh, that one's not going to go. That's the layman's physics. But I try to provide you with these because for a lot of people, including myself, the idea of electric flux is kind of hairy. Other than it makes problems easy to work when you know what you're doing with inside. Because this is where we actually want to get to. This idea of being able to generate an electric field between two plates. Because once we can generate a uniform electric field, we can create devices. And once we can look at that and manage these things, we can create devices. So the idea of flux helps to explain why charge is going to be on top of the surface of a conductor. The idea of flux will help us understand how the charge is going to concentrate at a point. And it's not necessarily just at a point. In fact, the other night with one of the thunderstorms that came in, if I have a thunderstorm and a thunderhead and you got it, the tighter the curvature is also where charge is going to come together. And that helps us deal with it helps us deal with our rods. Hang on, I have to share my screen again, because my other folks are not seeing it. And the idea eventually is that my electric field is going to control how my charges will move. Okay, so we're using this idea of flux. We go through and we develop the idea of flux. We can end up dealing with it, but we're going to do that so that we can deal with this part right here, that we can develop an electric field. Now, once we develop that electric field, we can do a lot of cool things. And this is what we're going to get into on Wednesday. And remember, by the way, that is a dot product. I don't know if you guys had been doing that in Physics 1. We have two kinds of products. We have a dot product and we have cross products. Our dot products lead to things like work. Remember, our dot product got us from going with forces dot distance. Remember, work was defined as my force dot distance. And that gave me work, which led to the energy work theorem. But if I did, and I'm going to write it correctly, if I did this and I did my cross product, that gave me torque. And torque is a vector product. So this gives me a scalar product. This gives me a vector product. Because what we're about to do is the exact same thing. So if I have a positive charge to a negative charge, and I create a uniform electric field, if I take a positive charge and I move it close to the positive side here, I had to do what? I had to do work, right? I actually have to do work I got to move that positive charge. And that's going to lead us to electric potential. All right, I'm going to stop there because I don't want to dive into electric potential. I want you to stew on flux a little bit. This is one of those concepts that I have a hard time explaining, so I'm being upfront and honest with you. But the ultimate result is this idea right here. And this becomes one of Maxwell's equations. We're ultimately going to get 4 equations. And that's one of Maxwell's equations that helps us develop light. And I'll try to answer questions. All righty. We'll see you guys Wednesday.